Let me try to plot it. It is some function like this. It is a parabola. Actually, it is a parabola. As you know, y is equal to x square minus some function, right? That is what is that parabola. So, try to you just assume this is a periodic function like this, because all our eigen functions are sine functions, right, sine n pi x by l. So, you can expand this, a n sine n pi x by n pi x, because I have made the, you can expand it, Fourier series. I am doing Fourier series. Have you seen Fourier series? So, this is the expansion you have to do. If you want, you have to find the coefficients a n, right. The coefficients a n are found by this coefficient a n is actually 1 by some 2 pi 0 to 1, actually 0 to pi, 0 to 2 pi, and then x into x minus 1 into sine n pi x. This is that integral. You have to integrate this, that function f of x multiplied by sine n pi x, integral from 0 to 2 pi will give me that coefficient a n's. You find all the coefficients. All the coefficients will be non-zero. How many coefficients will be there? All infinite number of coefficients. But they all will decrease. As n increases, the value will decrease, and that series is what people will call as a convergent series. Okay? Now, use that series, etc., and compute your h square average. You have to compute in that series. Now, that is like when you do the h square average for that series, so you will get an infinite series. Actually, you will get an infinite series, and the value will be some finite number. Since I have cooked up by other way, the value of that sum is equal to some 4 times n, okay? That is what you will get. Even though that series is very large, okay, it will be only 4 times n. It is like you can have an infinite series. You can have an infinite series whose sum is simply a finite number, and in some cases you can easily find a finite number. I will tell you one simple example. If I have an infinite series like 1 plus half x plus half 1 by 2 factorial half sorry x square, that is all. Okay, x square plus x cube. Let me consider this series. I want to find the value of this series when x is equal to half. When x is equal to half, what is it I will do? I will take 1 plus half square plus half cube, etc., etc., up to infinite number of terms. Now, what is the value of that? What is the value of that series which I am writing? This series is 1 plus half square plus half cube, etc., etc. There are 2 ways of finding it out. What are the 2 ways? Again, it is a geometric series. It is a geometric series, you know how to find it. But anyhow, I know the answer, because if I have this expansion 1 divided by 1 minus x, 1 divided by 1 minus x, if I expand it, that is what I will get. That series is what I will get. Okay? Now, if you sum all of them, you will get a number. I do not know what is that number is. Probably you may find it out. But when I put in this series, in this 1 by 1 minus x is equal to half, it will be 1 by half, which is 2. So, the answer is 2. Okay, you don't have to sum all the series, all the terms in some cases. Okay, so that is the idea. So even in this case of whatever I have done here, an, find the coefficients and then sum the series h square average, you will find it. Okay, and the answer is only simple what I have already given. So it is very simple to work out. Now it is more complicated. It is more complicated for several reasons about what I call as what I said. In fact, my friend was objecting to that. I said that there is a Hilbert space, you don't have to worry about it, it's only ordinary vector space, etc. This is the way I gave the lecture. He actually confronted me, how can you tell that? Because it is actually a more complicated mathematical structure. Don't bother about the issue, but the thing is, you can have 2-dimensional vector space, 3-dimensional vector space, or you have 2 components. A 2-dimensional vector space will have a column vector a1, a2. If it's a 3-dimensional vector space, a column vector a1, a2, a3. This is the way it will go on. There is no problem with many of these things. There are such matrices, you can multiply, etc., etc. As I told you, the problem becomes whenever that matrix becomes infinite in size. It's an infinite by infinite matrix, okay? And that becomes more complicated. There are several things which you have for finite matrices. However large that finite matrix is, it can have million by million matrix, trillion by trillion matrix. It obeys a simple result like trace of AB commutator is always 0. It does not matter how big the matrix is. But the moment the matrix is infinite by infinite matrix, that is no longer true. So there are several new things that happen because of this fact that there are infinite dimensional matrices which you have to deal with. Why is it you have to deal with infinite dimensional matrices? You can ask the question, said my wave functions are square integrable functions. I want to expand it in some basis, right? Any vector is expandable in some basis, right? You will write a1i, a2j, a3k, etc. You can write it. So if you have infinite dimensional space, you will write infinite basis will be infinite. That's what, in our case, sin n pi x by L, sin n pi x. Each function is sin n pi x. So n is going from 1 to infinity. So how many, the vector is infinite dimensional. If I want to write it as a column, I will write the first one is 1 0 0 0, second one is 0 1 0 0, and third one is 0 0 1, and up to infinite number of terms I will write. That is what that vector space is. Okay? Now whenever you have such kind of vector spaces like this example which you have here, there is some really funny things happen and it makes life little more complicated. And that is the origin of this kind of problem. Yes, please.
While calculating an, the limits are going from 0 to 2 pi or?
Well, actually 0 to 1 because I have kept the length of the thing.
Okay.
So usually people expand it in a basis with 0 to 2 pi because that is what the regular functions are. So that's the thing, it's 0 to 1 in this case. Or if you have 0 to a, it is 2 pi x by a. That's what will happen.
Sir.
Okay, anything else?
Sir, so when you said like psi star h square psi can be written as like the, since it is h is Hermitian, it can act upon psi star. I don't think it's right because I don't think it's correct.
Go ahead, I'm listening.
I don't think it is correct. Like if I do like integration by parts and then bring it out, it turns out to be still 0 because that psi is vanishing at boundaries, but psi, like derivative of psi is not vanishing.
No. H psi is chi. Psi star h is also only chi or chi star by definition, right? So this is Hermitian conjugate. H psi is chi. You agree with that? which means H is some matrix, psi is this column. So, this will give me a column, this is your chi. Okay. Now, H star or H is Hermitian, this object is Hermitian conjugate of that, which means it is going to be chi star. In this case it is not a problem because it is only real, chi star is same as chi.
But the moment we write a state vector or something like that,
So, that is what the meaning I have given.
we end up with some eigenvalues. The moment we write it in terms of
No eigenvalues here, they are not pure eigenstates.
No sir, like let's say if you try to write psi in terms of Fourier series, you have some eigenmodes plus a constant, and that constant will never vanish.
No, in this case completely you will get H, psi star H is only 2n, exactly you will have in this case. You can check it out, but I do not think you are right, because this object, that is why I wanted to introduce this notation psi H. In fact, we are going to use it again, this thing. So, this object is chi and this object is chi star, chi this way, that is the way it is. Okay, that is all that happens in this case. I can work it out for you if you have some patience, because it will take more time. I can work out from this also. I can sum that series also. Incidentally, I can sum that series because finally I know the number. I can find the sum of the series also. Okay? It is not very difficult. So, this is what you will get in this example. The reason why I am giving this example is only one reason. The reason is the following. So, the space of functions, square integrable functions is what I called as a Hilbert space, right. Let me call it as some big, any point in this space, in this thing is a vector in that Hilbert space, any point, okay, in that space. Now, you have some operator, let us say an operator like x hat. Okay. You have an operator x hat or p hat. Now, what is x hat? X hat operator acting on, let me take some function psi, I will have psi of x, I will have x times psi of x. This is the meaning of that operation, right. And I said psi is a square integrable function, which means psi star psi integrated will be 1 or finite number. That is what that function, square integrable function. Okay, psi of x is a square integrable function. If psi of x is a square integrable function, is it guaranteed x psi of x is square integrable function? Okay, that is simple question. If psi of x is some function, so the integral, this new function is x square psi star times x psi and then dx. This is the integral, right? X psi, x square psi star psi. That is what you should find out. Is it square integrable? That is a question. Okay? I will give you one example. One example is, for example, if psi, in order to say psi star psi integral dx from minus infinity to plus infinity, it should be less than 1 or less than infinity or finite number or 1. In order to make that as a finite number, the behavior of that function psi of x, okay, because there is a dx here. If psi star psi is not there, integral dx will come. Integral dx is infinity, right. So, the value of psi cannot be a number at infinity. It should go like, because this goes like x, very large value. So, the psi should go to infinity less than 1 by x power half, less than that, because there is a x power half will give you 1 by x, dx by x is log x, and log x also is infinity, okay, from minus infinity to plus infinity. That is what will happen. So, it should have something like, it should behave something like half plus some alpha here. If it goes like x power half plus alpha, psi star psi will be x to the 1 by x power 1 to alpha. That integral dx by x power something greater than 1, okay, this integral is finite. This integral is finite. Say alpha, anything, any alpha not equal to 0. It is always finite, because at infinity it goes to 0, okay, it goes to 0. So, this, because there is a dx which tells you that. So, if a function which is square integrable like psi f x, there is no guarantee x acting on that psi f x will give me a function which is square integrable. Okay. Now, this is true for not only x, it is true even for p of x, p, it is true for Hamiltonian various operators which you have. So, these operators which you have, they cannot act on all states in the Hilbert space. They cannot act on all states in the Hilbert space, because the resultant vector which you get is no longer square integrable. So, you act on some vector, it will go outside some other vector, but that is not square integrable. So, acting on this, these are all square integrable functions, but some operator here, it will go to chi, but that chi will be here. It goes outside that. It goes outside that. That is why we want to act on the square integrable functions, only a subset of square integrable functions in which this operator can act. So, that subset is called the domain of that operator. It is called the domain of that operator. It is that operator on which the wave vector, if it acts, it will not go outside the Hilbert space. Okay, it will not go outside. So, this is a problem whenever you have infinite dimensional vector spaces. So, if you have infinite dimensional vector spaces, an operator cannot act on, such operators cannot act on all vectors in that Hilbert space, all vectors in the Hilbert space, because it will go outside. So, it will have a subset of vectors in which you can act, and that subset is called domain of the operator. That is a very important point. Why is it very important is, we normally tell in colleges and courses, etc., you have an operator A, you find the Hermitian conjugate of that operator, right. I suppose this is what you are told. I am going to erase these parts. I am going to you have an operator A, I am going to define what is called dagger, a dagger, Hermitian conjugate. If you are given a matrix, how do you do it? You take transpose and conjugate. This is what, I suppose you know this, right? You say A transpose and conjugate. This is what you say is a Hermitian conjugate of that matrix or operator in that space. Is that known to everyone? Everyone in the back? So, then what you say, an operator is self-adjoint or Hermitian, okay, if A is equal to A dagger. If A is equal to A dagger, you say that this operator is self-adjoint or Hermitian. This is, I hope that statement is known, everyone? Yes or no? Please tell me. So, why is it we are interested in Hermitian or self-adjoint operator or thing matrix is the eigenvalues of this matrix, self-adjoint or Hermitian matrix, is always real. It cannot be complex. Okay, it cannot be complex. All operators which are self-adjoint or Hermitian, the eigenvalues are real. Now, we want to associate our observable like x, p, etc. When it acts on some state, expectation values which you try to find out, we want to get only real values, because it is going to be only combination of eigenvalues. So, all our measurements should lead. For example, when you look into the galvanometer or ammeter or anything, you are going to get a real number. You are not going to get the complex number there, right? So, the eigenvalues must be real. So, in order to have that, we say that all Dirac, when I said yesterday, he associated for every classical observable operator associate. X goes to x hat, p goes to p hat. That is the way he associated. They are called observables. When you say observable, the measurement of that operator will lead to a real value. That is why we want them to be Hermitian operators. That is one of the reasons. There are other important things. The eigenfunctions of these operators, these Hermitian operators, they are all orthogonal to each other. If you have two eigenvalues psi 1, psi 1 and psi 2, psi 1 star psi 2 integral will be 0. You do not have to do anything. It is almost like sine n pi x, sine m pi x. Let me make sine n pi x and psi m pi x. Integral from 0 to 1, if you work it out, you will find it to be 0. If you work it out, you will find that to be 0, right? Integral of that is 0. That is what you will have. So, these are all various properties of such operators. Now, these things work out correctly as you expected, whatever you have been taught, as long as you are in finite dimensional matrices, finite matrices. The moment you go to infinite dimensional things like this, it is not enough to say this is self-adjoint. We always say Hermitian is self-adjoint, okay? But that is true only if the matrix is finite dimensional matrix. If it is infinite dimensional matrices where you have all these problems, then there is one more condition needed to say it is self-adjoint. And that one more condition is the domain of the operator A should be equal to domain of the operator A dagger. These two conditions should be satisfied in order that operator is self-adjoint. If you do not have that, that problem will be there. So, that is one of the reason, which is also in this case, which affects all our problems. Okay? In this correction, I am going to give you one more exercise. That exercise is simply, I am going to give you a one-dimensional problem and ask you to find the energy eigenvalues. Okay? What is that problem? The problem is again R, which is minus infinity to plus infinity, and the potential, I have to give you the potential. I have to give you the potential, and this is a very peculiar potential which was cooked up by Dirac. and that potential is minus G delta function. Have you heard of delta functions? You have heard of delta functions? Those who have not heard of it, please raise your hand. Those who have not heard of it. You have not heard? Anyone? Others? Because I am going to give you a 1 minute introduction to delta function. It's 1 minute introduction to delta function. It's a actually mathematicians will not call it a function. Okay, but such a function is needed. So they will call it generalized functions. Okay? So we will use physics being like slightly loosely used. So we will call it as a function, delta function. This is what Dirac used, Dirac delta function. It's also the name. The function is, so in this interval from minus infinity to plus infinity, it is 0 everywhere else, everywhere. The function is 0. The function is 0. Okay? And at this point at x is equal to 0, it is actually infinity. The function is 0 everywhere from anything greater than 0 and anything less than 0, it is 0. And at x is equal to 0 is infinity. It's infinity. That is a kind of function. How do I visualize it? If you want, I have to draw one line here, one line here, one line here to say that is the function. At that point it is infinity, everywhere it is 0. Okay? That's what delta function. But to understand it better in a physics language, what you can do is you have the line from minus infinity to plus infinity, and you have a small width here A. At this point you draw a rectangle which is 1 by A. The height is 1 by A. The height is 1 by A, the width is A. So what is the area of that rectangle? 1. You take the limit A tends to 0. What is the area of that rectangle in the limit A going to 0? It's again 1. So that is what is the delta function. It is actually take this rectangle, squeeze it such that the area remains always 1. Right? Area remains always 1. That is the kind of function. Okay? That is the kind of function. So the interesting thing is, I have this potential. So it is minus, so the function is going to look like this. It's going to look like this. The value is g times that function. The interesting thing about that is, I am going to ask you to compute energy eigenstates of this. Energy eigenstates of this problem. Now, if it is simply that function is potential is not there, it is only free particle. It is only free particle. If this is not there, I can ask you to find the energy eigenfunctions of that operator. Now, what are those operators? What are the energy eigenfunctions for a free particle? Anyone knows? You want to find out h psi is equal to E psi, where h is p square by 2m, which is minus d square by dx square, apart from that h bar square by 2m. So you want to find out solution for this. Let me write h bar square by 2m, E times psi, or d square psi by dx square is minus 2me by h bar square psi. Okay, that is the equation you have to solve, and it is an equation which can be easily solved, and that equation is e to the power ikx, where k is that square root of 2me by h bar square root of that. That is what is the thing. Okay? So, that is the value of that thing. Now, is it a good function, wave function? Is it or not? Yes or no? No. No. How many people said no and how many people said yes? Is it no? Who else? No. Then there are a lot of half hands. Okay, fine. It is not a good function because it is not square integrable. If you integrate e power ikx psi star psi, as I told you, e power ikx into e power minus ikx will give you 1. Integrate it from minus infinity to plus infinity, you will get this. So, you cannot have that as a wave function in this thing from minus infinity to plus infinity. So, what I will do is, I will put that in a box from say minus L to plus L. Then within that, that is a nice function. Within that thing, outside it is 0. So, what you can do is, in general, a function like integral, okay, a function psi of x like integral dk e power ikx f of k, okay, that kind of function can be square integrable. Okay, that kind of function can be square integrable because I have put an fk. For large values of k, it can go to 0. So, this kind of function is called a wave packet. So, if that k is 0, you will have sine or cos function like this, sine or cos function up to infinity, e power I k is cos kx plus I sin kx, right, that is what you will have. So, that is not a good function for us because integral is not 1, square integrable. But if you have a function, like this, if you have a function like this, it is nice function. Okay, that is what you will create by collection of several waves, and then make it into a wave packet. It is not one wave, it is a collection of waves, and that is a packet, and that packet moves collectively together. That is what you can do. Okay, that is what you can do, and that is what is the wave packet concept, which is there always. That is what de Broglie wave, which he used, de Broglie wave packet. He had a group velocity, phase velocity, etc., comes from there. Now, given this, my problem is for this exercise, for this potential, which is delta function minus g delta of x, okay, find out the energy eigenvalues if it is there. But you should remember, it is everywhere is 0 potential except at that point. There are two ways of computing it. You can have this kind of a box which I have rectangle with potential height is 1 by a, the width is a. Find out what is there a bound state or energy eigenstate for that, and take the limit a tends to 0. That is one way of finding. It is more complicated way of finding, because if you have that kind of a problem, a box, okay, you have to apply the potential, solve the problem inside the box, outside the box, and then match the boundary conditions, But it so turns out that this problem can be solved without that kind of complication. And it is related to the kind of thing which I was always telling you about the nature of the wave functions, etc. And this is the answer. So, I will leave it at the moment as an exercise. Okay. Is that okay? Is that enough? I am going to start, already taken too much. So, I am going to start with other than particle in a box, I am going to start with a very simple introduction to harmonic oscillator. So, harmonic oscillator, okay, simple harmonic motion, simple harmonic oscillator, and I am going to solve the problem. Okay. I am not going to use the regular way in which the textbooks solve, but I will solve it in some little more matrix mechanics, which probably is good. So, the Hamiltonian is one dimension, p hat square by 2m plus V of x is half kx square, right. This is what is a harmonic oscillator. The spring constant is k, the mass of the particle is m, and if you pull that thing by the spring, it is connected to a spring, that mass will oscillate, it will oscillate. Classically that is what it will do. So, I want to do the quantum mechanical problem of this thing, which means I should find out solutions for this equation. Where this is actually h bar square by 2m d square psi by dx square plus half kx square psi is equal to E psi. This is the differential equation which you should solve for among square integrable functions. The function should be square integrable, which means whatever solution you should have, it should be, if you integrate psi star psi, it should be 1 or some finite number which you can normalize it always. That is what is required. So, not all functions satisfy this equation, and the solutions, do you know the solutions? Yeah, Hermite polynomials. It is more than Hermite polynomial, but with the Gaussian, yes. So, I will give you the solution, but I am going to not solve the differential equation, since in gory detail I will give you the solution. So, psi n of x, where n can be 1, 2, 0, 1, 2, 3 up to infinity, any number integer 0, 1, 2, 3 up to infinity. I will write down the solution, okay, in this basis, which is equal to 1 divided by 2 to the power n factorial square root. This number which I have put is the normalization constant, because the rest of the functions which I have given you, if you integrate it, you will get some finite number, you divide by the square root of that. That is what is the thing. And then you will have m omega divided by pi h bar to the power 1/4. It looks messy, but I will give you anyhow. And then e to the power minus m omega x square divided by 2h. There may be some typos here, 1 m omega square or something may be there, I do not know how to check. And then Hermite polynomials, which a friend mentioned, it will be some number by, sorry, m omega by h bar times x. Okay, that is the function. Now, this object Hn, it's written in gory detailed solutions. It looks little complicated. The Hns, Hn of 0, H0 of x is 1. H0 of x is 1. H0 of x is 1. H1 of x is 2x and h2 of x is 2 minus 2 plus 4x square, h3 of x is I suppose it is 2x or 12x minus 12x plus 8x cube. I have given some first 4 values 0, 1, 2, 3, but the number will go on up to infinity. N can go from 0 to infinity. That is the way of the harmonic oscillator. So, this is what is this thing, and if you are interested in doing only functions and calculations etc., you can sit and calculate this quantity and I will give you the answer. Do not even try to do that, it is a messy. There are other ways, simpler ways of doing, and you can find out the expectation value of x hat square between 0 and 0. This is what is meant by that is psi naught star x square psi naught integral dx. This is what is meant by that. That is what I have written down. If you do that, you will get the answer as h bar by 2m omega. And if you do that for p square, if you do that for psi naught square star minus d square by dx square psi naught multiplied by h bar square by 2m whole square and then dx. If you do for this, you will get the answer as m h bar by 2m omega, sorry 2, that is all. This is what you will get. Okay. Now, doing such integrals are not very difficult, and probably in the examinations they threaten you with evaluating many of these things. Okay. It is essentially working out Gaussian integrals. The integrals are of this form. If you have that integral from 0 to infinity or minus infinity to plus infinity, if I ask you to work out this integral from minus infinity to plus infinity, what is the answer for that? Root pi. Okay. Okay, he says it is root pi, let us believe probably it is correct. How do you get it? How will you get it? How will you find it? Either you look into the tables and then get the answer, or if I ask you to work out from first principles, like a regular integral, how will you do it? Anyone? Yes? Polar coordinates, that is correct. So, what is the thing is, you write down I square, this is I, then you will have minus infinity to plus infinity e power minus x square, e power minus y square, dx dy, you go to dx dy, you go to r dr d theta in polar coordinates, this will turn out to be e power minus r square integral. So, e power minus r square r dr is easy to work out, because you can say r square is t and then it is only integrating e power minus t from 0 to infinity. That is, and d theta will give you the 2 pi factor. Since it is square, it will turn out to be square root answer. So, this is the way in which all other things here with hn is very easy to work out. Okay. Supposing I ask you to work out this quantity, well, if I ask you to work out this quantity e power minus x square x dx, what is the answer? No, e power minus x square x dx from minus infinity to plus infinity. Anyone? He says it is 0. Anyone who is not agreeing or disagree have a different value? e power minus x square dx, x dx. Huh? What? Yes, x is an odd function and e power minus x square is an even. So, if you integrate it from minus infinity to plus infinity, you will get it to be 0, as simple as. So, if you have x square, you will have non-zero value. X square, if you have, you will have non-zero value, right? That is what you will have. How will you work out that? Yeah. So, that is the way which has to be done. So, a simple way is you write this integral e power minus alpha x square, no x square here, find this as a function of alpha, find this as a function of alpha, right, root by alpha, that is what you will have, right. It is the same integral, I am not doing anything more, I have only scaled x by alpha x, that is what I have done, okay. When you do that, you will get root pi by alpha. Now, if you want to get e power alpha x square, what is it you want? This thing, if you differentiate this with respect to alpha, you will have x square here, right. So, if you have the function I alpha, you can differentiate it with respect to alpha and put alpha is equal to 1. That is all, as simple as that. They are all simple tricks in integrations which you can do and get the thing, and any hns which you have, I have already given, the integral of those things with any powers etc. can be worked out. Any power of x power n integral can be worked out. Okay. This is only what is the functional things people will do, and I am not going to do that. I have given you this. And this is something probably many of you will know, people who have done the thing, but I am going to tell you a little more about it. What is the little more? Okay. I am going to define an operator instead of x hat and p hat. I am going to define an operator A. This is not a Hermitian operator. X hat is a Hermitian operator. P hat is a Hermitian operator. But this is not Hermitian operator, and that operator I define to make life simple. I will do some tricks later. M omega by 2h bar square root x hat plus I by m omega. I will tell you what is that omega is. This is the one. That omega is, omega square is k by m. This is the frequency of the oscillator. That is the frequency of the oscillator. The oscillator oscillates with that frequency. Okay. Now, in order to make life simple, I yesterday introduced my friend who was objecting, and I will, my colleague was objecting, you should not introduce such things at the BSc or MSc levels, and I will still do it. I will call h bar as 1. Okay? H bar is 1. I am going to do one more. I am going to make k is 1, m is also 1. Right? Mass of the particle is 1 in my hand, and the spring constant is also 1. It is also in my hand. So, the problem becomes simple. In that case, my Hamiltonian is half p hat square plus x square, as simple as that in that case, right. That is all the Hamiltonian. Where minus term? No, p is minus I h bar, but p itself, p square will have, the differential operator will have, but this will not have. Okay. So, p square is p is Hermitian operator, as I told you. So, if p is Hermitian operator, it has only real eigenvalues. It has only real eigenvalues. If you diagonalize it, it will have along the diagonal some real numbers. It may have -2, -3, +2, +3, all those things will be there. But p square is only square of those numbers, so it has to be always positive. Sometimes we call it as a positive definite operator, positive operator. What about x square? Again, it is both positive and negative values it can have. So that is also, square is positive, it is only positive. So p square plus x or Hamiltonian is a positive operator, positive definite operator. At most it has 0 eigenvalue and anything above that, but it cannot have less than that, right? It goes from 0 to infinity, but not from 0 to minus infinity. That is the kind of operator which you have here. Now, in this notation, A is equal to, if k is equal to 1 and m is equal to 1, omega will become 1. So this object which you have is 1 by root 2 x plus I times p. What I have done is p square plus x square which you have, or you know this, x square plus y square. If I define x plus iy is z, x plus iy into x minus iy will be x square plus y square. That is what I am going to do. So there is another operator which is a dagger. A dagger 1 by root 2 x hat minus ip. There are two operators which I have introduced, a and a dagger, which is essentially p square plus x square. That is what you go from Cartesian to polar coordinates, right? R is that x square plus y square, right? That is what is there. That is what I am doing here. Now, we know that x operator, p hat operator, commutator is I. I have taken h bar as 1. That is what your Heisenberg commutation relations tell you. So I can find out what is the a dagger commutator. You can find out, okay, and take it as an exercise, and many of you know the answer. Answer is 1. It is 1. It is 1. It is actually 1, and that Hamiltonian which you have here is a dagger a plus half, half times this one. Am I right? No, a dagger a plus half. This is what the operator will turn out to be. Okay, it will turn out to be this operator, a dagger times a times plus half. As simple as that. So instead of operators x hat, p hat and Hamiltonian, I have made into a dagger and h, which is a dagger a. So this is what the operator is, and I want to find out h psi is equal to e psi. Solutions for this equation. Yesterday somebody was asking me, you said x hat is a matrix, p hat is a matrix. I am going to give that matrix now. I will give you that matrix now. Now first let us find out eigenvalues of this operator. Now the eigenvalues of this operator, essentially I will call m as an operator which is a dagger a. We will call that operator as number operator. We will call it as a number operator. We will see why it is number operator. So what you will find is, if you have some state, I will call a vector m, which is essentially something like infinite dimensional somewhere, some maybe 0, 0, 0, 0 and 1 here, 0, 0, 0. that kind of vector, okay, infinite dimensional vector. Because I told you all our vector space is infinite dimensional, I will have various vectors up to infinite number of components will be there, and the nth component is 1, the rest of them are 0. So let me take that kind of a vector. Or a linear combination of that. The interesting thing you will find is, if this n is an eigenstate of A dagger A, if it is an eigenstate of A dagger A, with eigenvalue, let me call it as some n itself, with this number n, you can call it a function of n if you want. You can call it a function of n, you don't need the thing. Then A dagger acting on this n will be a new state n prime. It will be a new state n prime. A dagger is going to give you a new state. The n prime is also an eigenstate of A dagger A. N prime is also an eigenstate of A dagger A. The question is, what is its eigenvalue? The eigenvalue of that is 1 above n. So if I have said n here, it is f of n plus 1, f of n plus 1, or if it is n, it will become simply n plus 1. So A dagger will rise, it will go one ladder above, in the ladder one step above. You act by A dagger square, you will go one more steps, 2 steps above. A dagger cube will give you 3 steps above. What about A? A will do the opposite. So A acting on n will give you n prime, n double prime, let me call it n double prime. This A dagger A acting on n double prime is n minus 1. N double prime. So what does it do? A lowers it 1 unit, etc. You might have started with 2.5, it will go to 1.5 and then 0.5, etc. But after acting by 0.5, okay, it will go to minus 0.5. A dagger A will be minus 0.5. But I have already told you that A dagger A or Hamiltonian is positive always. It cannot have any negative eigenvalue. So which means it should go to only 0 eigenvalue. The lowest eigenvalue of A dagger A has to be 0. Anything below that, nothing will happen. Okay? So that is a kind of thing which you have here for this problem. So you will have A dagger A acting on n, give you n times n, where n is 0 to 1, 2, 3 up to infinity. And A acting on that state gives you n minus 1 state, n minus 2 state, and A acting on 0 gives you 0 because of this thing. So A acting on 0, gives you 0. It kills it. People will call it as a vacuum state or ground state, the lowest state. You cannot go below that. Okay, that is the ground state, A acting on 0. So what you have actor acting by A dagger, 0 will become 1, 1 will become 2, 2 will become 3, etc. on that ladder. If you start somewhere else in some 10, by acting by A, you will get 9, 8, 7, 6, 3, oh I missed, continue correctly, go up to 0. You can't go below that. So this operator, A dagger, is called rising operator. It rises. And A is a lowering operator. In the ladder operator, it's called ladder operators. In the ladder, it one is rising and another is lowering. If you do further, you will find some people call it as a creation operator. If there is one particle, one quanta, it will become 2 quanta, 3 quanta, 4 quanta, and A will be reducing it. If there are 4 quanta, it will become 3 quanta and 2 quanta, etc. One is called creation operator, another is called annihilation operator. And n, A dagger A, gives you the same operator. Okay? So, if you take a book on quantum mechanics by the Japanese physicist called Sakurai, in his introduction, he calls this A operator, A dagger operator, and N operator, as A is in Hindu mythology, you have Shiva who annihilates, and A dagger creates Brahma, and Vishnu provides whatever prosperity we want. He called it as the Trimurti. The A dagger and N are the Trimurti. He, in that book, I was surprised that this guy from Japan is talking about this, but it was interesting. So, this is the way in which these 3 operators act on. It is called Sakurai quantum mechanics book. So, this is the nature of these operators. Okay. So, somebody wanted, what is my X? Is it a matrix? And I am going to give you the matrix, because my states are, so I can erase all these things. The lowest state is the ground state 0, I call it 0, and I am going to write the vector. This is my vector for that 1 0 0 0 up to infinity. That is my ground state. You cannot go below that. What is the next state you can go? 1 is 0 1 0 0 0 0. That is the next state. And 2, I will erase here and write it. I will erase here, write it here. The third position, fourth position is 1. That is the collection of vectors. Any vector is a linear combination of them. Any arbitrary vector will be, write A1, A2, A3 up to infinity. That is all. Which means, if I write any state sign is an n, it simply means a1, a2 up to a, somewhere an and somewhere a infinity also. Okay, that is all that is there. That is that vector. Now, in that space, I can write down my A's and A daggers. Let me write down the A's and A daggers. Let me try to run a little fast. Am I going very slowly or fast? You have to tell me. You have to tell me, am I going very slowly, or for him it might be slowly, might be knowing already, but for some people also. But I am trying to average out. So, the operator A dagger, it is a matrix. I told you it is a matrix. It transforms one vector to another vector. What does it do? A vector with nth number, n position is 1, it transforms to n plus 1. That is what is the thing. And I will write down A dagger for you. That matrix is 1. It is actually 1, root 2, root 3, root 4, etc. Okay? That is why is it, where is that root 2, root 3, all those things come? In order to see that, you have to find out A dagger acting on n. If you actually work it out, it will turn out to be root of n plus 1 times n plus 1. Why is it so? N may be normalized. Your state N may be normalized. N will be, I will write it this way, this notation 1. But A dagger N, and then this is what is this state is supposed to be, and then complex conjugate of that is this. If I do this, this is some N plus 1. Okay, you have to take the square root of that. So that's what will happen. So this is the result. So which means the connection between nth state and n plus 1th state, there is a factor of root n plus 1. Similarly for, and here I will write, these are not real. A, the operator A is same matrix, just take the transpose. A dagger, if you take the conjugate, you take the conjugate and star. But here it is enough if you take transpose and star, but it is enough if you take the transpose because it is a real matrix. It is 1 here, 0, 0, 0 here, root 2, 0. Diagonal terms are 0. The diagonal terms are 0. Off diagonal terms in the first off diagonal, just above the diagonal, they are all 1, 0, 1, 2, 3, 4 up to square root of that. And similarly. Now we have this definition which I gave you A and A dagger. From that I can write down x hat operator. X hat operator is an A plus A dagger, apart from 1 by root 2 or something. Okay. So it's only, I have given you two matrices, A and A dagger. Just add the two matrices. That is your x. So yesterday somebody was asking me, is x is a matrix? Answer is yes, x is a matrix. The operator x is a matrix. Similarly, the momentum is a matrix operator. In acting on the space of states which are labeled by 1 0 0, 0 1 0 0, 0 0 2, all those things, collection of all such states, you take it in that space, your x hat operator is simply this. Simply add. It will be Hermitian automatically. It will be nice operator which you want to have. Okay, this is what is the operator x hat is. Okay. So this is the whole thing about harmonic oscillator problem, which is very simple, and I gave you to start with eigenstates in terms of e power minus x square, etc., etc. How do I get them from here? Okay. I told you in matrix notation, Heisenberg notation, you may want it in the terms of Schrodinger representation. To do that, it is very simple. It is very simple. It is very simple. A acting on 0, the ground state is 0. A acting on 0 is 0. But A I have defined for you earlier. It is some 1 by root 2 x plus IP acting on 0 state, the lowest state is 0. But now you know what is P hat. It is minus IH bar. So this is here plus d by dx. IH bar, H bar I have taken to be 1, minus I and plus I will make it as plus 1, and this is the thing, and this is, I will call it as psi 0, the ground state. You don't need this root to here. This is a simple differential equation. It's a very simple differential equation. It will be x plus d psi by dx. X psi is, d psi by dx is equal to minus x psi. That's all that equation. You solve it, answer is e power minus x square by 2. It's a Gaussian. It's called Gaussian. E power minus x square by 2 is the solution. The solution is, you can solve this and you will get psi naught is equal to e power minus x square by 2, apart from normalization factors. Okay? Now you got what I gave you in the exercise thing. I gave you general solution psi n in terms of Hermite polynomial, etc., etc. How do I get the next one? You act on psi naught by a dagger. But a dagger is what? I have already given you the thing, differential operator. You act on that by x plus x minus ip. You act on that, you will get a new function. That's your next high one level above, 2 levels above, etc. All of them can be easily worked out. So this is one way of solving, is what was Schrodinger equation. Solving is a differential equation. And another way of solving the same set, same thing, is by Heisenberg mechanics. Okay, one is Heisenberg picture, another is Schrodinger picture. That's all, as simple as that. Okay. There are some interesting things that can happen now, and that's what I wanted to tell in the next 5 minutes, and then I will slowly move to the angular momentum. I want to start with angular momentum today and then get some idea. Okay. I have, the states are, now I am going to have a new Hamiltonian in 2 dimensions. What is the new thing? It is half px square plus py square plus x square plus y square. I will have the frequency for both the oscillators same, one and the same, which means 2 oscillators. Instead of 1 oscillator, it is 2 oscillators. As simple as that. Now can anyone tell me what is the eigenstates? What are the eigenstates for this problem? It is simply adding one more, right? Whatever you did with x will happen for y. So the x has set of eigenvalues given by n, right? Eigenvalues are given by n plus half. Now y will have again another n. Instead of calling it as n, you call it as m. So the general state is going to be labeled by 2 numbers, n comma m. One for x, one for y. One for x, one for y. Okay? So this is going to be n comma m, and the e will be n plus m plus, so you had n plus half and m plus half. So it will be n plus m plus 1. It should be multiplied by h bar omega. It should be multiplied by h bar omega. For my unit, h bar is 1, omega is 1 for my unit. Otherwise, you should put that also. So what are the eigenvalues now? N plus m plus 1. A state is n comma m, and the eigenvalues are n plus m plus 1. Is that clear to everyone? Because I am going to ask further questions. If you say yes, you should answer also for the question. Better say no. Is that okay? You are ready? So what is the lowest state? Ground state? 1. What is the state? How will you label it? N is equal to 0, m is equal to 0. So let us write down that. So you have the state n is equal to 0, comma 0, and the value is 1. E energy is 1 unit, h bar omega, 1 unit of h bar omega. What is the next state? Higher 0, higher than 0. Yes. So you can have n is equal to 1, n is equal to 1, or m is equal to 1, and the value is 2. Value is 2, correct? Agreed or disagreed? Yes or no? Yes. Next state is 1 0 0 1. There are two states now. There are two states now and both have value 2. We will call it as degenerate states. Something very nicely degenerate states. Okay? From this exercise I am going to do several things which is going to bother about next, yes, tomorrow and day after also, tomorrow as well as angular momentum. So let me go further down. What is this next one? 0 2 2 0 and then 1 1. Let me call it as 1 1 first and then 2 0. Okay? You can have n is equal to 2, m is equal to 0. You can have n is equal to 1, m is equal to 0, 1 and n is equal to 0, m is equal to 2. The total is how much? 3. Okay? So, energy eigenvalue 3 has 3 states. Energy eigenvalue 3 has 3 states labeled by 0 2, 1 1 and 2 0. Energy eigenvalue 4 will have how many states? How many states? 3 0, 2 1, 1 2 and then 0 3, 4 states. Energy eigenvalue 5 will have 5 states, etc. Right? This is what you have. So the number of states, degeneracy of the thing goes by 1 unit above. It has 1 state, 2 states, 3 states, 4 states, 5 states, etc. for this problem. So the degeneracy here is related to certain things inside that Hamiltonian itself, because there is nothing, there is an x, there is a y. You can put 2 here, 0 here, or 0 here and 2 here, or 1 here, 1 here, right? That is what, it's like 2 boxes. In the 2 boxes you want to keep number 3 chocolates. So you put 2 chocolates in 1 chocolate here, put 3 chocolates here, 0 chocolate here, or something like that, that is all. In fact, probably in statistical mechanics classes that is what he did, right? Probably, I do not know, has he started something like this in statistical mechanics? No, not yet. Okay, fine, he will probably do it, because what is it you are going to have? You are going to start with the number of states in that box which you have. That is what you are going to have. So this is a very interesting thing to start with. Okay. So this is the way the whole thing is going. Okay. I don't know whether I am going to start now, and what I am going to start is about angular momentum. Have you heard of angular momentum? R cross P, R cross P. Now the angular momentum value, probably you might have heard, it is specified by a number j, and j can be 0, 1, 2, 3, 4, any number. The number of states in that is 2j plus 1. Are all the people aware of this? If you have done hydrogen atom, this is what you will have, 2L plus 1. Let me not call it J, let me call it as L. You will have angular momentum is specified by L, and ground state will have 0, no degeneracy. The first state, L is equal to 1, will have 3 states, 2L plus 1. The next one will have 5 states, 2 into 2, 2L plus 1, that is what we will have. Now that is what is happening here. Ignore these things. Ignore these things. The next one you all the even things you ignore. All the odd things you have, 0, 3, 5. It looks like some angular momentum coming up, right? Angular momentum coming up. Now you might have heard of spin angular momentum. Electron has spin value which is half, and it can be spin up or spin down, two states. So in addition to angular momentum r cross p, if you have a spin also for electron, hydrogen atom, the states will be, it can be half, spin half, which is again those omitted things which I have here come out in that, right. The two state is only spin up and spin down. And the next one 0, 2, 2, 1, 1, 2, 0 is like spin value, angular momentum value is 1, which has 1, 0, minus 1. It's what is that? Okay. In fact, if I say, if I tell you, you take this n, you take this m, you take this n minus m, half of n minus m, okay. So what is half of n minus m for this? It is 0, right. For this, there are two states here, n minus m is what? N minus m is minus 1, right. Half of that is minus half. And the next one is n minus m is 1, n minus m is 1, half of that is half. It's like plus half and minus half, spin up and spin down. Now let us go to the next one. What about 0, 2? N minus m is minus 2, half of that is minus 1. So it is minus 1 state, it is minus 1 state, 0 state, and plus 1 state. You go to the next one, it will simply match. So the angular momentum things automatically come here in all these things, okay. And that's going to be my next theme. Where is that angular momentum built here? Angular momentum is related to rotations, right. Angular momentum is related to r cross b is related to rotations. I can understand rotations between x and y, but it's not a 3-dimensional rotation, it's only 2-dimensional rotation. Whereas we find what you have in 3-dimensional rotation is appearing here. Where is the 3-dimensional rotation coming from? That is the symmetry which is there already, and I leave it to you, think about it, where is it coming from, and if possible today afternoon I will be here for the tutorial. If I am around, I will come, I will explain that part. Now I am going to the angular momentum. Remember all these things because it will come up again. Okay. Okay, let us go to the angular momentum. Angular momentum operators, or you have heard in classical mechanics, is given by r cross p. You are aware of it, right? This is your angular momentum operator L as a vector. So let us write down. Lz is going to be xpy minus ypx, and Lx is going to be ypz minus zpy, and Ly is going to be zpx minus xpz. These are the operators. These are the dynamical variables in classical mechanics. You know this, right? R cross P. Now what I want is make them operators. So I am going to put them as operators. It's only putting the hat. all of them you have here. So take it as an exercise, which probably you have done earlier. Find out what is Lx, Ly commutator. Lx, Ly commutator. Now I have given that as operators, right? You know the relation x px is I, y py is also I, z pz is also I. The rest of them are 0. The rest of the combinations are 0, right? So you can sit and compute, at least once you should do that. You can find out for one, Lx, Ly. If you find for Lx, Ly, you can easily find for Ly, Lz, you can find for Lz, Lx, Lz, all those three things, because it's only change x to y to z. It's a cycle, okay? So at least try to do one, Lx, Ly commutator. Anyone knows what will be the answer? Because you have studied in, yes? Lz. So now my h bar is 1 in my unit. That's why I have put I here. Otherwise I should have put h bar. So this will be I times Lz. Okay. So that is what is the angular momentum. So now I should find out matrices corresponding to that. Because I have already found out matrices for corresponding to x hat, p hat, all those things. Now I should do for these things also, because now they are all operators. Okay? So I will write down in some nice notation. I will write down in some nice notation. So you have three operators, Lx, Ly, Lz. And they are all operators. None of them commute. None of them commute. Lx, Ly is not 0, Ly, Lz is not 0, all those things. So you can't make all of them diagonal. If you make them diagonal, they will all commute, right? You can't make all of them diagonal matrix. At least only one matrix you can diagonalize. You can make it as diagonal. One of them you can make it diagonal. There is no problem with that. There is no problem with that. So let me make Lz diagonal. Lz is a diagonal matrix. It will have some number of states. Okay? So it will have some, let me call it as m. It will have m eigenvalue. It will have eigenvalues which are m. I don't know what is the number value m, but that's what it will have. Lz is diagonal for me. Okay? To start with. It will have positive, negative, etc., etc. Now there is one more. That's the interesting part. I compute what is called L square. Lx square plus Ly square plus Lz square. I call it L square, and then I find out the commutation relation of L square with Lx. Okay? L square with Lx. What will it be? Anyone? Anyone? Why are you hesitating to tell? It doesn't matter if it is wrong. 0, right. It will be 0. What is it you have to verify? You have to verify at least one matrix, Lx. Enough. And it has to be 0 because Lx is doing a rotation. But it's like x square plus y square plus z square will not change whatever rotation you do. Right? X going to x cos theta plus y sin theta, all the rotations you have learnt already. Whatever rotation you do, x square plus y square plus z square is invariant, doesn't change. What Indumati might have told us, x square plus y square plus z square minus c square t square. Something which is invariant, it will not change, right? So here also it will not change, so this is going to be 0. Similarly for Ly, Lz, right? Similarly for Ly, Lz. So this operator called L square commutes or does not have anything. So L square with Lz is also 0, correct? So, if LZ is diagonal, I can also make L square diagonal, because both are commuting. Commuting matrices, if they commute, you can diagonalize both of them simultaneously. That is probably something which I should have mentioned, that is there. So, it should have some value, and for all practical purposes, we will call that number L square the state, and I will put that eigenvalue of that as J or L. I will call it as L into L plus 1. Do not ask me why this funny L into L plus 1, that is what comes out. Naturally, it is there in your hydrogen atom. L into L plus 1 is coming out, all because of this guy Legendre. He gave the polynomial, he did not get simply L square, he got L into L plus 1, okay, and that is what comes out. Okay, so now you have a basis. The states are labeled, and I am going to stop here with this thing. L square acting on Lm gives you L into L plus 1 times Lm. Lz acting on L comma m gives me m into Lm. This is the basis, because you have diagonalized both of them. What are the things you are left out now? You have Lx and Ly, right? Lx and Ly. And the interesting thing which you did with the harmonic oscillator, I will define L plus as 1 by root 2 Lx plus ILy, and L minus as 1 by root 2 Lx minus ILy. I will define L plus and L minus. Why is it I am defining this? Because my knowledge about As and A daggers gives me something like that will help. And the interesting thing that helps is, by using the same algebra which I have, which I call it algebra, angular momentum things, I will probably help you in the afternoon. The result is, if you start with m, L plus acting on m will go to a new state, that is also eigenstate of Lz, just like what you had here. N you started with, A dagger acting on that goes to n plus 1, but that n plus 1 is also eigenstate of A dagger A, right, Hamiltonian. Like that, if you start with an m state here, if you start with Lm and L plus acting on that will give a new state, let me call it as L m prime, but the eigenvalue of this state, that Lz acting on L comma m prime will be m prime m plus 1. One step above, it is a ladder operator, it just takes you one step above. Okay. L plus square will take you 2 steps above, L plus cube will take you to this. So, L minus will lower it one by one. Okay. The most interesting thing is, unlike the case of A dagger A, etc., where it went up to infinity, here it cannot do that. It has to stop at some lowest value and it has to stop at some maximum value. It cannot go above that. You can't go above and below. I will explain why it is so. So, it will actually go from minus L to plus L. The m value can be only from minus L to plus L. So, if L is 1, it can go from minus 1, 0, 1. If L is equal to 2, you will have minus 2, minus 1, 0, 1, 2. That is your state, number of states is 5. Okay. If you start with 3, minus 3, minus 2, minus 1, 0, 1, 2, I can't go above 3. So, there are 7 states, 2 into 3 plus 1. So, that is what is going 2L plus 1. All the matrices which you have now, L plus, L minus and Lz, or Lx, Ly, Lz. These 3 states, these 3 operators are finite dimensional matrices. Unlike the previous case where you have infinite dimensional matrices, here you have only finite 3 by 3 matrix, 2 by 2 matrix, 5 by 5 matrix, etc. That makes quantum mechanics even easier because you don't have to deal with infinite dimensional matrices. You don't have to deal with infinite matrices. It is enough if you deal with finite number of them. But that finite number can be very large number because L can be million. Then 2 into million plus 1 states will be there. Okay? So that is what is the idea. So this is what is our angular momentum minimal introduction, and then I will tell you more about some of these things if possible in tutorial and tomorrow also. And then if I do it in tutorial, I will, if possible, otherwise tomorrow. Then I will take up time independent perturbation theory, which is also related to this. For example, I gave you the degeneracy of level 1, level 2, etc. So I add x square plus y square on my potential. I add some x square y square potential, another potential, or x thing. Or if I make it as x square instead of y square, I put 4 times y square. So the degeneracy will be lifted. Okay, it will not be degenerate again. So that is a kind of a thing which will be of interest. Okay, so I'll stop here, and you can go for coffee. And if possible, I'll take some tutorial along with the other students, and you can ask me any question. You should come with questions. If you don't come with questions, I will ask questions.
Is everybody inside? Can we start? The audience is showing a decaying function. Is it too simple or too hard? Huh? Interesting. That's why they don't come. No, it's not correct to ask the people who have come, right, about people who are not here. So, anyway, so do you really all want to stay in the back? Then, okay, I guess you will see the screen on the top, right? How many of you have just finished second BSc? Okay, so the others are all okay. So okay. How many of you have finished third BSc or more? Okay, the bulk of the people. Okay. So yeah, I saw your hand. Good, raise it like that, like you've actually eaten breakfast. So the thing is, so when you say you've seen Maxwell's equations, you've all done electrostatics, magnetostatics from school onwards. You've seen Maxwell's equations in integral form? Everyone seen Maxwell's equations in differential form? Who hasn't seen Maxwell's equations in differential form? Anyone who hasn't seen Maxwell's equations in differential form? So are you all comfortable with Maxwell's equations? Is there somebody who wants a quick review of Maxwell's equations? Huh? No, look, I mean, I have no portions to finish. I want you all to go away with at least, there's no point in doing some advanced stuff if the basics are not ready. Okay, fine. I can see that there are some faces who want to say yes and are not willing to speak out. So let me give a very quick review. So before I start the review on electrodynamics, I actually wanted to stop with the Lorentz group and transformations, but I found that I need one more property. So let me go over what I said in the last class. So we were talking about tensors and vectors. So 4 vectors and 4 tensors, and tensors. So we had defined, I hope all of you remember, contravariant and covariant vectors depending on their transformation properties, right? So let us see who remembers. So if I put, I think I called this A and I called that B, let me not change the notation. So this was called A and this was called B. So this is the primed variables and they will be related to the unprimed variables. So what will be so let us put all the, now you have to tell me what is coming where, right? So let's look at A prime alpha. If it's contravariant, what will be at the top? X prime alpha, very nice. So this bottom let's just call it beta. So once this is beta, this will also be beta. And you remember that when we have repeated indices, they are summed over, right? So that means A0 will be related to dx prime 0 by d0 plus dx prime 0 by dx1 plus dx prime 0 by dx2 plus dx prime 0 by dx3. I hope this is very clear what we mean by repeated indices. It's not just one quantity, it's a whole series of 4 terms, right? Okay, so what happens with the covariant vector? So x is on the top, x prime comes below. The indices don't change, right? Beta is below. So alpha is on the top, beta is below. So, okay? Huh? Oh, sorry, yeah, you're absolutely right. It has to be B beta. Thank you. Yeah, there is no transformation that takes A to B, not Lorentz transformation. So, okay, and the tensor we had defined. So you keep going this way. You have series of indices, right? I called it F alpha beta. So the primed variable will have two indices to lower it. So this will be, because it's above, this will be prime, this will be prime, this will be alpha, this will be beta. Let's call this gamma and delta. So this will be gamma and delta. So I guess you can do the covariant thing as well, right? I am not going to write it all. What happens if I didn't do this? Yeah, only one variable will be. That's your choice, right? You can do whatever you want, but this will not be the same f variable because the Lorentz transformation, if this is prime and unprime refer to a Lorentz transformation, then of course this is incomplete. But as tensors, you can always define contravariant and covariant vectors like that. And then I defined a B dot A as either B alpha A alpha or lower alpha A upper alpha. And that was because, if you remember, I actually showed you that I have a special object called the metric tensor G alpha beta, which is the same as G lower alpha beta, which you can simply check from this definition. Check that the G upper alpha beta and G lower alpha beta are the same, and this is equal to the diagonal matrix of 1 minus 1 minus 1 minus 1. This is because we have taken x alpha to be Ct xyz. Some books will define x alpha as xyz comma Ct. Then in that case you will have the metric tensor will have minus 1 plus 1 plus 1 plus 1, but it's your choice. It won't make any difference to the physics, okay, as long as you know what you're doing and you have a consistent set of definitions. So because of this, I can use G alpha beta or G alpha beta. So G alpha beta will raise a covariant vector and G lower alpha beta will lower a contravariant vector. So if I make x alpha G alpha beta, so alpha is summed over, beta is not. So what should I expect on the right hand side? I'll get x covariant beta. Now you can see the notation helps. By putting the covariant indices on the bottom and the contravariant indices on the top, you can see that for a proper dot product, which is a scalar, which means it's invariant under Lorentz transformations, you can check that this will be invariant under, what does this give you? Do you remember? If I take x alpha, what does it give me? X alpha covariant times x alpha contravariant will give me ds squared, right? S squared, which is the invariant distance between x1 and x2, right? Or 0 and x in this case, right? Because it is an invariant, you can see that if one index is above and the other is below, and if this index is below, the other side index also has to be below. So you simply have to make sure that you match these indices. So the number of indices above on the left hand side must be equal to the number of indices above on the right hand side, okay? And you can immediately see therefore that x beta, it's very trivial because it gets multiplied, this is diagonal, right? So it will get multiplied by 1 for Ct and minus 1 for the others. So it will be Ct times minus x minus y minus z. So in general, if I label the upper index x alpha, this is a repeat of the last time as x naught, x1, x2, x3, and the lower index by x naught, x1, x2, x3, then I will have x naught is equal to x naught. So I'll never actually worry about the 0 component, but x1 will be minus x1 and so on, right? You can see that, right? It's trivial. This is upper x1, this is lower x1. So when we use the notation 3 coordinates x, y, z for the 3 vector component of the 4 vector, we are referring here to the contravariant part. X, y, z belongs to the contravariant set. Minus x minus y minus z will belong to the covariant set, okay? Is this clear? Because there is a little hitch here. You think of writing suppose I want to convert, like yesterday we did, right? We wanted to write d by dt prime in terms of d by dt, right? So what did we write? D by dt prime is d by dt into dt by dt prime. That is the chain rule. So suppose I write the chain rule for, so d by dx prime alpha. I am not doing a Lorentz transformation here, but I want to simply rewrite this derivative in terms of d by dx, not d by dx prime, using the chain rule. So how will I do it? This will be equal to d by dx alpha, or not alpha, what index will I use? Let's call it beta, because I don't know that it will be the same, times dx beta by dx prime alpha, right? It is exactly like d by dt prime is d by dt into dt by dt prime, right? And there are 4 indices here, right? So let me just actually write it interchange. This is just a number, right? So I am getting this from the chain rule. But then you look at this. What does it look like? Does it look like A or does it look like B? Huh? It looks like B, right? So that means naturally by construction, the derivative is a covariant object. Those of you who are in MSc may have heard of covariant derivatives, right? They are always covariant derivatives because they transform like a covariant vector, right? Is it clear? So this, I will therefore give the symbol d alpha, lower. And then therefore I will write d alpha lower is d by dx. See, it was related to d by dx upper, always the x's are upper x's, right? D by dx1, d by dx2, d by, so this is what I missed out yesterday, it's very important. So you can see that I can call this x0 is c dt, right? So this is 1 by c d by dt, and what is this remaining part? What are upper x1, x2, x3? So what is d by dx, d by dz vector? Huh? It's a vector, right? It's a 3 vector. d by dx, d by dy, d by dz. Gradient, very nice. This is a gradient vector, right? Is it clear? I hope you have seen all these before, right? Gradient, curl, everything. You can't write Maxwell's equations without gradient and curl, right? So, fine. So what will happen with the upper alpha? Now I don't have to compute anything anymore. You now know that x0 will remain the same, and this will become minus del, right? And immediately you know in quantum mechanics that del operator is related to the momentum operator. So you will see that unlike the space coordinate, the momentum operator, the positive valued momentum operator will be covariant and the P upper alpha will be contravariant, right? So this is something that is different from what you usually have. I'll give you an example of the continuity equation. You have seen the continuity equation. If I have a charge distribution rho, this is a charge density and a current density J, then the continuity equation can be written as d rho by dt plus del dot J equal to 0, right? I hope everyone has seen the continuity equation. What does this mean? That if I have some volume, because this is all densities, right? I have some volume in my mind, and whatever charge is changing in this volume over time is actually going out as a current flow, right? This is true whether it is electrodynamics or whether you're talking about water flowing, right? Sorry? Probability, yeah. So the continuity equations occur everywhere. It's just a law of conservation of whatever, this is the current density, it could be the flow density, it could be probability density, anything, right? So now you can see that here I have, let me put, that side is anyway 0. Now you look at the del operator and you can see something over here. So if I define now another 4 vector which is j alpha, which is rho comma vector. Okay, whenever you cannot see my vector sign, I put the arrow, otherwise I just put underline for vector. So don't get confused, they are the same thing. If I think that you cannot see it, I actually put the vector form. So if I define the 4 vector current J, and I already have the 4 vector del, then you can see that equation is nothing but d alpha j alpha equal to 0. Is it clear? Can you see that? So the minus sign, minus of the minus sign becomes plus, right? Because that becomes the lower component is plus del and the other guy would be also plus. So this bookkeeping really helps you in making sure that you get your signs right. That is the main reason you write everything in 4 vectors. You can see that this is now manifestly invariant, right? Alpha alpha, now you know that they are proper 4 vectors. So that means d alpha j alpha is a scalar and the right hand side is a scalar. So you can see this is manifestly Lorentz invariant. So by just reconstructing everything in terms of manifestly invariant quantities, you will be able to say that yes, electrodynamics actually is invariant under Lorentz transformation. You don't have to do those horrible Lorentz transformations and then go wrong in the factors and the signs and things like that. So that is what we are trying to do now. So this is one thing I wanted to tell you, that you have to be a little careful with del. The other thing I want to tell you is, which is something that I will use. So it is a little bit mathematical right now, but as I said, I'll need that a little later. So I might as well do it when I'm talking about Lorentz transformations. Is we are now writing some x prime in terms of x, and x prime is a 4 vector, x is a 4 vector. So I can now think of a matrix representation where my x prime alpha is a 4 vector. So its x prime is this. Okay, and I can write x prime therefore is related to x through some matrix. This is your Lorentz transformation matrix. So for example, it will have gamma times, so this will be x0 prime in terms of x0 will be, so gamma times t minus vx by c squared, whatever. So all those entry elements you will be able to write, okay? Fine, you understand this, right? So now that I have a matrix, I can immediately talk about x transpose. So what will x transpose be? X transpose will be a row vector. So I can now do matrix multiplication, right? So what do I mean by x alpha, x alpha? So when I say x alpha, I mean row times a column, which is simply a number. Right? So how do I convert the column into a row? By multiplying by g alpha beta, right? So I can nominally call this scalar product as x comma x with a g in front of either this one or a g in front of, I can do anything, right? I mean, because I can have x upper alpha, x lower alpha, whatever. So I can simply write this as, so any dot product, any dot, not just x, let me just put some a and b, dot product of a and b, I can write as this, where G is the matrix of G alpha beta, right, which is simply diagonal 1 minus 1 minus 1 minus 1. Now why am I doing all this? So what is the special property of a Lorentz transformation? That x alpha is an invariant, right? So all the Lorentz transformations are under the constraint that is, which is actually just s squared, right, is an invariant. So now let me write, so x prime is equal to, what have I given it as? I have given it a name A. So A is a 4 by 4 dimensional matrix. I hope you can see that, right? If this is 4, then this is a 4 by 4 matrix. Okay. So now I know that under the constraint, what is the constraint? That x prime gx prime is equal to x gx. So how do I multiply this? I have to convert one into a row. So I can write it as x prime transpose gx prime is equal to x transpose gx. So now I can, x transpose is simply this row matrix, right? That's why I defined it. But what is x prime? X prime is ax, right? And this is ax transpose. What is the formula for AB whole transpose? So this will give me x transpose A transpose G times A times x. And this has to be x transpose G times x. So what can I tell you, what can you all tell looking at the board? Very nice. Somebody is awake. And there are many more things you can do with it. I am sorry I cannot, in 5 lectures tell you everything about everything. I don't even know everything about everything. I just want to take determinant on both sides. What is the property of product of matrices? Determinant? Huh? Very nice, it can be multiplied. So determinant of ABC is determinant A into determinant B into determinant C. And what is determinant of A tilde and determinant of A? No, not one, they are not inverse. They are the same. If you transpose a matrix, its determinant remains the same. A is a square matrix, remember, okay? Fine, determinant of A transpose, you're looking at it like this, you're looking at it like this, whether it's rows or columns, you don't care, right? So this is the same as determinant of G times determinant of A squared is equal to determinant of G. So what can you say about determinant of A? 1. Very nice. I can't see who said that, plus or minus 1. Okay. Now you can check by saying you can use x prime is the reflection of x, or x prime is the time reflection of x. When I say x, I mean 4-dimensional x space. So when I say time reflection, x0 prime goes to minus x0, right? Or the space reflection when xyz goes to minus xyz, right? You can try all such things and you will find that they all will have determinant of the transformation, because you can write the A, right, and find its determinant. It's very easy to do that. And you will find that those constitute the determinant A minus 1 subset. But the determinant A plus 1 subset are what are called proper Lorentz transforms. So this is what I want. So plus 1 are called proper Lorentz transforms, and they will include the boosts that we are talking about. Boost means transformation from one inertial frame to another inertial frame, and rotations also. Okay. So the Lorentz group will contain both determinant A plus 1 and minus 1, those who know a group theory, otherwise just forget it. And determinant A plus 1 is what we will use sometime, either most likely tomorrow. Okay, so please remember it till tomorrow. But once I am doing this, I wanted to just finish this part of things. Is it okay? So no, let's not say more about it. I think you can always read more, right? You don't need me to tell you this. Okay. So before I give a brief review of Maxwell's equations, let us try to guess what are the 4 vectors in the theory, because I am claiming now that I can write a manifestly Lorentz covariant Maxwell's equations, one set at least, and therefore I should be able to write everything in terms of 4 vectors, right? Then I know that it's manifestly Lorentz invariant. That's what I want to show. So already we have so many 4 vectors, right? So let us see what all we have. We have x alpha, right? Then we, of course, for tensors we found g alpha beta. Then what else did we find? Huh? 4 momentum. 4 momentum. So we had first started with u alpha, I hope you remember. In yesterday's class we showed that the velocities are not, I mean c comma u does not form a proper 4 vector, but gamma times c comma u forms a 4 vector, right? Right, so this, and m times that will give you the 4 vector p. Now you can see that you can also write p in terms of d by dx, but you remember that, right? We wrote d by d tau, right? So the m d by d tau of this u alpha will give you p. So we also saw, let me write it, so this can also be written as right. What is P alpha? P alpha? Sorry, now I have to somewhere put PC. Sorry, the C equal to 1, sometimes when you put back the C's, yeah, this is correct, yeah. So what is P alpha? P dot P? It has to be an invariant, right?
Isn't it E by C?
Huh?
E by C in the 4 momentum?
Doesn't matter, you choose. Somewhere the dimensions have to be the same, right? PC has dimension of energy. If I put E by C, then the E by C has dimensions of P. Depends on your definition, no? Who cares? I mean, it's a constant. C is a constant. It won't affect the transformation properties of that vector. Yeah. So what is P squared? Very nice. So is equal to, so this is, I said yesterday was, because I put the C here, it will be C power 4. If I had put the C here, it would have been m squared C squared. Please put the C's back correctly. The units of energy are E, PC and mc squared. So I want you to also do as homework, please make sure those are the units of energy. Make sure that mc squared has units of energy. Make sure that PC has units of energy. PC you know because energy of the photon is PC. So you know that has units of energy. E of course is energy. And you make sure that mc squared has units of energy. Right? So this units and dimensions are very important. If you know how to deal with units and dimensions, you can guess a lot of answers just by looking at the dimensionality of the problem, right? Okay, so where were we? Yeah, so 4 vectors. So okay, so this comes, so this is also equal to m times u alpha, right? What are the other vectors? 4 vectors we know. Huh? We just wrote j alpha, very nice. So j alpha is again rho and j. So you can either put 1 by c here or you can put c rho, one of the two places. It's your choice, right? So what is, this is not enough for electrodynamics, right? There are more things in electrodynamics. Huh? Electric and magnetic field. How can I make a 4 vector of electric and magnetic field? Right? See, what all are there? I have to have all these quantities, right? So I need to write, this is a 3 vector. I need to find some partner of these 3 vectors to find a 4 vector, right? And it will turn out that actually you cannot do it. Okay? And actually it will turn out that E and B will be components of a tensor. You remember F alpha beta I introduced, right? So actually E and B are elements of a single second rank tensor which is called F alpha beta. And the elements of F alpha beta will be E and B. How many components are there in F alpha beta? 16, right? It's a 4 by 4 matrix, right? Alpha goes from 0 to 3, beta goes from 0 to 3. You can think of a matrix as 4 by 4 matrix, right? Right? But I now say that this is an antisymmetric tensor. I'll show you later why. Suppose it's an antisymmetric tensor. Then can you tell me how many elements are there? Huh? Don't give me formulae, no? I mean, substitute and tell me. Right? What is an antisymmetric? What are the diagonal elements of an antisymmetric tensor? 0, very nice. So have a 0, 0. So we have already solved for 4 elements, right? What else do you know about antisymmetric tensor? So you have, what is left over here? 1, 2, 3, 4, 5, 6, right? What do you know about an antisymmetric tensor? What is negative? Transpose is negative. So where is the transpose? Suppose this is the 0, 0 element, this is the 0, 1 element, right? So what can I say if I know 0, 1 element, what else will I know? 1, what will be 1, 0? Very nice. So how many elements are there? 12, no, you just told me that these are the same, right? With a minus sign. So how many elements are there? 6. And how many elements are there of E and B? 3 E's and 3 B's. This is not higher mathematics, right? So there are 6 components of E and B fields, and those will become the 6 elements of this antisymmetric second rank F alpha beta. And we will get there. We will see how we can actually construct the F alpha beta, which contains these E and B fields. Then we will be able to rewrite Maxwell's equations in terms of F alpha beta. Okay? What else have you studied apart from E and B fields in electromagnetism? I will just go give a quick overview, but this will just tell me like how much you remember of the stuff. Huh? What else is there? That's all. I can't hear. Who was it who was saying something? Yeah? Potentials, very nice. That's what I was looking for. So what are the potentials you know about? Vector and scalar. So boom. Can you put them together? How will you put them together in the 4 vector? So can I call it A alpha? I think, okay, fine. I won't swear to it, okay? Is it clear? So if you see a potential which is scalar and a potential which is vector, you hope that they will transform like a 4 vector. So all these, by the way, you have to check. You have to check the transformations. But once you write it all in terms of completely covariate notation, it will become extremely trivial to check these things. So I'm not going to check it right now. We will do the simpler version later. So these are the kind of quantities that are appearing in your magnetic field and electric field as different combinations. And now you can understand what you would have learned in electromagnetism is that once you have a moving charge, so when I have a static charge, that's a whole chapter called electrostatics, and its electric field is Q by R squared. But once that charge starts moving, you know that it generates a magnetic field. And then Faraday found that if I have a changing magnetic field, then it generates an EMF, which then therefore gives rise to an electric field, right? So you can see why that happens, because the transformations of F alpha beta, now you can see what will happen to F alpha beta prime. How will I write F alpha beta prime? Dx alpha prime by dx gamma, dx beta prime by dx gamma, F beta gamma, right? So it will mix up all the elements. So the E field will mix up with E and B field, right? And therefore, it turns out that when you move from one frame to another, if I am in the frame where the charge is at rest, I have pure electric field. When I go to the frame where the charge is moving, then it immediately generates a magnetic field that comes out naturally by looking at Lorentz transformations. Is it clear? So the reason we are doing all this, so before I start writing all this and you wonder where I am going, what we want to do is actually rewrite it in these terms so that we will have a very good handle on looking at these kinds of transformations, and we'll be better able to understand how these electric and magnetic fields so-called mix, and moving charges can give you magnetic fields and moving magnets can give you electric fields and so on, okay? Fine. I don't need to rub it. Okay. So now let me do maybe, let's see if I missed anything. No, I don't want to do all this. Yeah, you can do lots of things, but I don't want to do it. Okay. Maybe before I proceed, I don't know where exactly I will use this, but rho over here, right? This has a very fundamental implication. If I take a charge density, which is localized in some small space, and I integrate it over all space. So I make sure that I cover all the places where the charge density is distributed. What will I get? Total charge, right? So rho d cubed x. So provided I haven't missed anything, is just the total charge q. Right? Now what we just say is that q is a Lorentz invariant. See, we don't have any transformation laws of q. Okay? The charge is the charge. In whatever frame I look at it, you can just think of, suppose I have a bunch of electrons here, then some 10 power minus 19 coulombs, so many of them are there. And in whichever frame I look at it, they are 10 power minus 19 coulombs, right? So the charge is an invariant of the Lorentz transformation. And therefore this left hand side, rho d cubed x, is an invariant of the transformation. But then you see that rho d cubed x looks similar to a 4-dimensional volume of our space time, which I can write as the usual 3-dimensional volume times the volume due to x naught, right? So this whole song and dance about determinant A being 1 was that if I transform d4x to d4x prime, then it will transform to dx naught prime into d cubed x prime. Okay. Now let us assume that only dx prime changes and dy and dz are the same. Again, I am doing the simple case. Now you remember, if you want, you can put all your equations. You know how x prime looks in terms of x and y, t prime looks in terms of t. You don't have to do all that. Just remember that time dilates. Time dilates by how much? Gamma means gamma in the numerator or denominator? Right? And length contracts by how much? And so what can you say about this? This is an invariant. Okay, this is now just my hand waving argument. You can write this, when you write a transformation from d4x prime to d4x, you can write d4x prime is equal to the Jacobian of the transformation times d4x. I hope you have seen Jacobian in 3 dimensions. If I take xy and replace it by r theta, then I get a Jacobian of the transformation, which will be x naught prime, x2 prime, etc. divided by x naught, x2. So this is just the determinant of this matrix, right? And this will become the determinant of, so I am not going to do it, you can ask someone in the tutorial to do this. This becomes determinant of A times d4x, and therefore I have just shown you that for a proper Lorentz transformation, determinant A is plus 1, and therefore d4x prime is equal to d4x. Okay? So since here I have explicitly used the proper Lorentz transformation, I already got plus 1, but in general you can show that this comes out to be plus 1 for proper Lorentz transformations. So now that brings us back to this. I can therefore write d4x as dx naught times d cubed x, and I know that this is an invariant volume. This is an invariant. This, by virtue of being a charge, is invariant, and therefore you can see that rho has to transform like the time component of a 4 vector. Is it clear? And this is why we are putting, this is why we put rho as the time component of the 4 vector. Okay? So such insights are many. This is just one example. There is something about J, but I think I will skip it. There is something about A, I think I will skip it. Okay, so let me just do this review first, because we have talked about so many quantities. Let us just do a review and then we will continue. Okay. Because I just want to set the notation, otherwise you will not know what I am trying to do. When I rewrite the Maxwell's equations in 4 vector form, at least you should know them, right? So this is all right, right? There are no questions on this? It's all okay? Fine. So here is a brief review. Well, anybody's, but ultimately Maxwell's electrodynamics, right? Okay, where do I start from? Okay, where will we start from? Tell me, what is it you know about Maxwell's electrodynamics? Let's start with electrostatics. What do you know about electrostatics? Huh? Gauss law. Okay. You don't want to start with Coulomb law? I hope you know that Coulomb law is the physical law. Gauss law, what is the difference between Coulomb law and Gauss law? Okay, tell me what is Gauss law, tell me. What is Gauss law? Huh? One person. See, you must understand, I can't hear from this side. No, I don't want words, just give me some equation, right?
Then integral E dot dA
Huh?
integral E dot dA is equal to Q by epsilon naught. Okay.
Oh, okay, you want epsilon. Okay, fine. Okay, fine. So let me start with I will come to your Q by epsilon naught because I want to write so my rho d cubed x is your Q. When I integrate over all space, I will get E is equal to, if you want I can write a simple equation, E is equal to Q by R squared into unit vector R, right? Right? But I hope all of you understand that electric and magnetic fields are imaginary quantities, right? They are not something that I can measure. What do I measure in the lab? I measure Coulomb's force law, right? I can only measure forces between objects. I have two charged objects, Q1 and Q2, and the force between them is given by Coulomb's law, and we write the force is equal to, what is the relationship between the force and the electric field? The electric field is the force on the unit charge, but nature doesn't give us unit charges. Nature gives us electrons, protons and maybe quarks, but not unit charge, right? I hope you realize that a unit charge is a huge quantity. Do you realize unit charge is a huge quantity? What is the electron charge? 10 power minus 19 coulombs. So if you had an object which was 10 power 19 times of that, so it's like a very, very large charge. So we don't have such charges in nature. So the electric field is a convenience. Same way magnetic field is a convenience, right? It's the forces that you measure. So forces are measured and therefore you talk about field lines. It's not as though there is actually a line drawn somewhere, right? These are all mathematical constructs which are convenient because you don't always want to talk about the other object, because force means I'm talking about another object. When I talk about the field, it is the field at one point. I'm not worried about where the other object is, right? So these are conveniences and therefore I have converted this equation to this equation. And he actually had an integral form. That's, in fact, I was wondering whether that this is something that is, so how do you convert the left hand side to an integral form? So I say that here I have a volume V. So let me draw a volume V. This is my volume V. And let us say that the charge is located somewhere here. It's concentrated around the point x prime, right? So this is let me think of one point x prime over here. And it's the electric field due to that charge is here. This is E, right? And if I now want to integrate it, I define at this point, I define a normal and I say that this is theta with respect to that normal, right? So then what do I get? I get the normal component of the field. So this is the field, which is just Q by R squared, right? The magnitude of the field is Q by R squared. So Q by R squared into cos theta, because E dot n is just cos theta. So the perpendicular component of the electric field on the surface, so this is the surface S, is simply Q by R squared cos theta, Q by R squared cos theta, right? Now I say that I want to look at the field in a little surface dA. I want to sum up over all this whole surface, right? So I want to sum over this surface by integrating over this little dA. But how do I understand this dA? Let me write dA like this. Suppose I have in 2 dimensions, if I have an arc of a circle, then this is theta, and if this distance is L, let me call this distance as L, and the distance from here is capital D, then theta is equal to L by D, right? Now if I write this in for a little segment of area, then this will be called the solid angle d omega, and if this distance is D and this area is dA, then d omega is equal to dA, maybe since I have used r over there, I will use r over here, by r square, right. This is a normal area. Now I do not have a normal area, I have something which is at an angle theta to it, right. So then this will now become dA cos theta, right. So you can see that dA cos theta by r squared, I can write it as equal to q d omega. Now I integrate both sides. What is integral of the solid angle? 4 pi, right. So this is, of course, if it is outside, if the q is outside the sphere, I will get 0. That is what Gauss's law tells me, right. Now what do I do to the left hand side? So now I have, this is called the first integral form of Maxwell's equations, E dot n dA over the surface of this volume is equal to 4 pi times the charge contained in the volume that it encloses, right. How do I get a differential form of this? I am only giving this in detail, after that I will just say, oh, similarly, 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 okay. So we are doing this in little bit of detail. So how do I convert this into a differential equation, huh? Yeah, I use Gauss's theorem. I use Gauss's theorem which says, see, I just don't know, there may be some quiet people who don't know this, so I don't want to, because they are quiet, I don't want to miss it out. So Gauss's, what does Gauss's theorem say? That if I have a function del dot f over some volume d cubed x over a volume V, then I can write it as the surface integral of f dot n over that surface area, right. So now I am going to apply it backwards. So the left hand side now will become del dot E d cubed x over some volume is equal to 4 pi rho d cubed x over the same volume, and therefore if I look at the integrants, because I can bring it to the other side and the volume element is not 0, I can say del dot E is 4 pi rho. So for those of you who have seen the equation in MKS, you would get rho by epsilon naught, right. This is in natural units, because I don't want to have epsilon naughts all over my equations, okay, or mu naught for that matter, fine. So this is the first equation, and we just got it by looking at distribution of a localized charge, right. So maybe we will put it somewhere over here. Del dot E is equal to, so okay, so then what do we do? Shouldn't have rubbed off this equation. Let me just keep it. Always, it's nice to write equations where you can see, right? So suppose now I have a static magnetic field. How will I write B of x? Just by looking at that equation. Similar, right? Again, B is, what will you write? Instead of rho, what will you write? Very nice. So you will write J of x prime, and because that is a vector, you will write cross x minus x prime by, it's a 1 by r squared law, right? See, this has a dimension 1, so if I make it a unit vector, it is just 1 by r squared, right? And by the way, this in my units, there is a 1 by c. See, these units you have to just fix somewhere, okay? And you hope that the textbook got it right. Okay. So how do I get the second Maxwell equation from this? Can anyone see? I have an A cross B, and do you know the property of, what is this a function of, the right hand side? What is the right hand side a function of? X, right? Everyone, x prime is a dummy integration variable, right? So it is a function of x, but the integration variable is x prime, right? So it is not integrating over x. So can you see that the derivative of 1 by x minus x prime is exactly minus of this quantity, right? So I can write this as there's a minus sign. It's not del prime. It is del means it acts on x and not x prime. And I hope you can see that del prime of this is minus del of this, because this is x minus x prime, right? So if you add del on this and if you add del prime, it will act on this, it will give you minuses of each other, right? And I can remove the minus sign by putting, right? Del is acting on, right? Now this J is a function of x prime. Only del has x minus x prime, right? So I can write this as because it doesn't care about this, right? Sorry, cross. Clear? From this immediately, how do I get second Maxwell's equation? I can hear people saying something, but no, because the left hand side is just b of x, right? Very nice, just take the divergence, right? So I have b of x is equal to, so let me write it schematically. I have b is equal to del cross of something, which is just a number, right? It will just be a function of x. So I take the divergence on both sides. Let me call it f of x, it doesn't matter what it is. Why is this 0? Why is this 0? Always del dot del cross is 0, right? Right? I hope, by the way, that you know how to do these cross products in terms of epsilon ijk, and you are not writing matrices. Sorry, this is an aside. When I write, let's not take a and b, not even x and y. Give me some variables, not r is the distance, s and t, okay, let's take s cross t. Okay, so how do I find the element? Let's take 3 dimensions, let's not worry about 4 dimensions, we are still dealing with del in 3 dimensions. How do I take a cross product of 2 quantities? Let me say that I want the I goes from 1 to 3, I want the ith component of s cross t, that can be written as epsilon ijk Sj Tk. Has everybody seen this? Because when we write it now in 4 dimensions, otherwise you will, not be able to do any of these calculations, right? Fine. So you can use this to prove this equation extremely straightforwardly. So now we have, fine. And therefore we can write B is equal to del cross A. So this whole thing will just become A, right? Because del dot del cross A will be 0 and that will satisfy del dot B equal to 0. That's how you get your vector potential, right? Fine. So this is okay? Now what are the Maxwell's equations that are left over? Yeah. So I have to get I have got del dot of two things, now I have to get del cross. Let us start with del cross B, because we already have the expression for B on the board, right? So I am going to write B is what? B is that object over there, right? So now I have to find del cross B. So that is 1 by C del cross. What was B? B is del cross J by x minus x prime. Integral d cubed x prime. And in fact, I could have put the integral. Let me put the integral here, because del is outside the integral, right? So what is the formula for del cross del cross? So, okay, I think at this point I should give you 3 minutes to just derive it in your notebooks, right? Use this formula. So you will have del cross S. So first you write del cross S, ith component in terms of epsilon ijk, or write the jth component, and then from there, so this then you call this as some t. So then you find del cross t ith component. Okay, will you please do this and see what you get? So this j prime just means j of x prime, okay? I am just being short with my notation. Okay, shall I move ahead? Is that okay? That this is the formula that I wrote on the right hand side? Okay. Now I already told you that del acting on this denominator is the same as minus del prime acting on this denominator. Okay. And I'll put a bracket here, because now I have to be a little careful. Why should I be careful? Because now this is d by dx prime, and this also contains x prime. But right now, because this was acting on this quantity only, It is still only acting on that quantity. I have not done anything else. Okay. Then now what I will do is I will do an integration by parts and convert del prime to act on j. So I will get plus del of del prime dot j prime x minus x prime. Okay. What is this? J prime is independent of x. So this is simply del square of 1 by 1. Write it here. What is del squared of 1 by mod of x minus x prime? Has anyone seen this before? Huh? Yes, it is the Dirac delta function, right? No one has seen this before. How did you do this calculation in the class? Okay, fine. If everyone is looking blank, so let's forget x minus x prime. Let's just call it x. Okay, then we can always shift the origin to x minus x prime. So what we want to show is that this is equal to delta cube functions, function of x minus x prime, right? So the way to see it is like this. Let us start with r is the magnitude of x, right? What is the divergence of 1 by r? Can you quickly calculate it? What is r? R is root of x squared plus y squared plus z squared, right? So let us just think of it. You always think of the one variable thing, right? So 1 by root of x squared plus y squared plus z squared. And you are doing, let us write d by dx of this. How will you get d by dx of this? Just d by dx of something to the power of half is something is half, something to the power of, so this is like d by, let's look at d by dx of something to the power of minus half, right? So it will be minus half, something to the power of minus half minus 1. So this will be r cubed, right? And then the derivative of this object, which is 2x, right? And so the 2's will cancel, and so you will only get, it's a vector quantity, you will get r by r cubed. Is this clear? Everybody understood this? No? Is it okay? Okay? Fine. Now, you can see that once I have a 1 by r, if I take x equal to y equal to 0, then this whole thing blows up, and therefore there is no meaning to the statement unless r is not equal to 0, right? So you can see this immediately that the non-zero quantity is only coming when r is equal to 0. When r is not equal to 0, you have only this quantity. Now I have to do one more del on this, right? So when I do one more del on this to get del squared of 1 by r, now there are two quantities. There is r dependence in the numerator and denominator, and please do it as homework. Again we will take r not equal to 0, but when you do all the calculations you will get 0. Is it clear? You have to do this. It will be some 3-4 steps because you will have to differentiate numerator, denominator, use various rules of differentiation, but when you add them all up you are going to get 0. Just explicitly you are going to do this. So take this result and do one more del on it to get del squared of 1 by r. So how do you deal with the quantity at r equal to 0? What you do is that you take the integral over some volume, finite volume, and this finite volume must include the origin. So it can't be any arbitrary volume, but it is some volume that includes the origin. Then what is del squared? I can write this as del of 1 by r dV. Now I have rubbed it out, but you know that integral over volume of del dot f can be written as f dot n dA, right. So this will be integral over the surface del of 1 by r dot n or dot dA, whichever may be dot n, I have been using dot n dA. But what is del of 1 by r? Here minus r by r cubed, right? That is equal to minus r by r cubed dot n dA. Now what is the little volume element in 3 dimensions? Yeah, d cos theta d phi, right? So if you don't know d cos theta, sin theta d theta d phi, right? So I can remove, just call it a unit vector and make it r squared. So the r squared will cancel. So I'll be left with only cos theta d phi, which is the solid angle d omega, which will give me 4 pi. Right? And this contribution is coming from the origin, because you know that it is 0 everywhere except at the origin, right? Because we have always taken this to be 0. So if you want this equation and this equation to be consistent, then the entire non-zero result has to come only from r equal to 0, and therefore you have to put the delta function. So when r is not equal to 0, so this will be, you will read it as d cubed of r, right? Because I have just done of r, right? I mean, you can convert everything to r minus r prime, it will be the same result. So you can see that when r is not equal to 0, then the answer is 0, which is exactly what we have got over here, right? When r is not equal to 0, the answer is 0. But when r is equal to 0, then this will become 1, and the answer is minus 4 pi. Is it clear? So this is therefore minus of minuses plus 4 pi. I have integral j of x prime delta of x minus x prime d cubed x prime. Is it clear? So what is j of x prime delta of x minus x prime? I hope the delta is clear. It's a delta cubed. It means delta of x minus x prime, delta of y minus y prime, delta of z minus z prime, right? It's a 3-dimensional delta function. So what is in 1 dimension f of x minus x naught delta of, or let's write f of x delta of x minus x naught dx when the volume element contains x naught? What is the answer here? F of x naught, right? So the same thing in 3 dimensions, this will just be j of x, right? Clear? Clear? Is it okay? Fine? Okay, so this part we have got. Now we have to still deal with this first part. What do I have to say about it? Okay, so now we have 2 solutions, okay, and I would like to split it into 2 parts just in the interest of not deriving all of electrodynamics all over again in 2 days, okay. The first solution is that I have here del prime dot j prime, okay, but we know that in steady state magnetostatics del dot j equal to 0, steady currents, right. So let us just solve that first, then we will put Ampere's displacement current afterwards and correct for it. So what will happen? You will just get del cross B is equal to 0 plus 4 pi j. Actually there was a 1 by c, so I should get a 1 by c j. And it will be easier to correct for j, the displacement current, rather than to solve this integral when del dot j is not equal to 0. That's why I already showed you the continuity equation. What is wrong with del dot j equal to 0 in the general case? What was my continuity equation? del dot j will be minus 0 by dt, because I had d alpha j alpha equal to 0. So, del dot j is not 0 in general, but it will be related to minus 0 by dt. But what is minus 0 by dt? Minus 0 by dt will be related to d by dt of del dot e. And there is a del dot here, there is a del dot here and the del dot there. So, I can write it as del dot of j plus dE by dt. So, that is my Ampere's displacement current. So, now that if you can see it immediately, let me just write that down and be done with that equation. So, plus, so there will be that 1 by C sitting because you are substituting here, or it will not, yeah, dE by dt, right. So, now we have remove all this. Okay, I think what I will do is, so let me just write it here first. So, del cross B was 4 pi by C. So, you can see that in this form of writing, my elements of j alpha are rho and j by C, okay. But you have to just have a consistent set, right. So, this came from writing del dot j is minus d rho by dt and substituting d rho by dt as del dot dE by dt, right, that is what you get. So, this is the modified Ampere's law by Maxwell, which poor thing, he just did one thing, and but everything is now called Maxwell's equations, right. So, now the last one has even more complications. So, I am just wondering, okay, I will just give an outline of the equation, and I will leave it to you either in the tutorials, or if you think you know it, you can forget about it. So, what is left over is the final equation for del cross E, right. Sorry? Right. So, where does this come from? Faraday's law. So, we have to talk about time varying fields. This is exactly why those equations were not enough and we had to add this portion, right. So, what does it say? That if you have a changing magnetic field or a coil current, which is essentially a changing magnetic field, then you generate an EMF, right. And that EMF is then proportional to the flux which is linked with the circuit, right. So, what is the flux? Flux is given by, so it is related to the time change of the flux which is B dot A, right. So, B dot N dA. So, over the surface of the circuit. Now, you can see how abstract these concepts of E and B are, right, because it is not as though there is a physical something there, you are integrating over some circuit which can be anything, right. Now, you have to do many things. You have to write d by dt as partial d by dt plus v dot del. Has everybody seen this? If the motion is with a velocity v, why? Because if you have some function of x and t, then d by dt of this is d by dt into dt by dt plus d by, I have taken only one dimension, into dx by dt. dt by dt is 1, so that is d by dt plus dx by dt is the velocity, and if I take 3 dimensions, that becomes del, right. Is it clear? Fine. So, I have to account for this motion part, okay, and then I have to do many things, and I do not think I will do the many things. Okay, let me just write outlines of the equations. So, I will get a line integral of E dot dl, okay, and that will come out to be minus 1 by C d by dt of this B dot n dA, which I have written on the top. Now, I use Stokes' theorem to convert this into a del cross E dA, right. So, now I have written always dot n. So, my area element has no this thing, is minus 1 by C d by dt of B dot n dA. Then I can actually write del cross E is equal to minus 1 by C d Sorry, this will take longer and I don't want to spend that much time. So I kind of fast forwarded it, but I've told you where it comes from. Okay. So this essentially tells you that when I have a changing magnetic field, what did Faraday find? When he moves a circuit or switches on or switches off the current in the circuit, or he brings a magnet close to the circuit, then an EMF is generated in the circuit, and that is the EMF. So it has to be time changing magnetic field, and therefore it is related to dB by dt. So dB by dt comes because you have time changing magnetic fields. dE by dt comes because you have time changing current charge densities, right? That is the source of these two terms, and this is the Maxwell's equation. Sorry for fast forwarding. This is a little bit long derivation. So maybe someone who wants can ask for it in the tutorial, right? So I want to move on from there. So we have our 4 Maxwell's equations. So maybe I should say a few words about them. So the two equations, del dot B equal to 0 and del cross E. Can you see? Actually I don't need to, I have not written it in the right order. Okay, I will write it again. These are the two homogeneous Maxwell's equations, and del dot E is equal to 4 pi by C. Either it is 4 pi by C or rho by epsilon naught, I don't care, and del cross B is equal to 4 pi by Cj plus 1 by C. Let me write it the other way around. Minus 1 by C dE equal to. These are called the inhomogeneous equations. That's basically the right hand side here involves the charge and current density distributions. In the other one it is 0. So they are the homogeneous solutions. Okay. If I then maybe I should simply also include over here when I am saying all this, we have B was del cross A, that doesn't change, but because of that extra piece, E was minus del phi for static fields minus 1 by C dA by dt. That comes from that extra term that we have got. So you can substitute these quantities and check your definitions. Okay. So then I can write my electric and magnetic fields in terms of the scalar and vector potentials. Now you have to notice one thing, the relationship between the B and E fields, ultimately these are related because Q times E is the force, right? So these are ultimately related to the observables, are related to first order derivatives of the potentials, either the time derivative or the space derivative. Which means that if I add constants, either time independent or space independent constants appropriately to A and phi, the E and B fields will not change. That means I can only determine A and phi up to these constants. Okay, so there is a certain arbitrariness in A and phi, and you will have heard of this as something called a gauge transformation or a gauge fixing. Okay, so all it means is that because I can add things to A and phi and not change. For example, if I, you know that, okay, let me give a specific example. So because of this, there is an extra freedom in this definition of A and phi. But before I go to that freedom, let me just, you can substitute over here, you can substitute for E and B in terms of the A fields, which is A and phi fields, and I will just get out of the way the fact that when rho is equal to J equal to 0, I hope I have written that equation somewhere, yeah. So you can see, when I substitute, for example, del dot, del phi will give me del squared phi and so on. So I will get things like minus del squared phi plus 1 by C d by dt of del dot E is equal to minus 4 pi rho, and then del squared A minus 1 by c squared t squared A minus del So I have just substituted, okay, you can just substitute. I copied it because I didn't want to make mistakes. Okay. Now, this contains A and phi and this contains A and phi. So there are two sets of coupled differential equations which I want to decouple. So what do I have to do? I have to substitute something somewhere. So first thing I do is that I shift A, so A is a vector A to A prime. This is not a Lorentz transformation. Now this is simply a gauge transformation, and the reason I can do it is because I do have that freedom in this definition. Simultaneously I shift phi to phi prime, sorry, A goes to A prime, which is A plus del lambda, phi goes to phi prime, which is phi minus where is the c, sorry, 1 by c d lambda by dt. So you can see immediately, for example, the extra term will be del cross del lambda. Del cross del is 0, right? So the extra piece that you have added is 0. Same way here you have had it. So here you will add d by, okay, here you will add d by dt of del lambda, here you will add del of d by dt of lambda, and the two terms will cancel each other, right? So E and B will remain same E and B. But you see what happens to this extra piece over here. This extra piece becomes 0. So I will have 1 by c d phi by dt plus del dot A. C dt is x naught, del is x1, x2, x3. So this is simply d alpha A alpha is equal to 0. Suddenly I have brought back my 4 vectors, but you can, otherwise you will never remember what this is. You will remember it because of this, right? That is the power of this 4 vector notation. So with this constraint, this goes away. This becomes an equation only for del squared A. Then you can solve it and substitute back here, because now del dot A will be related to minus 1 by c d phi by dt. So when I put del dot A as minus 1 by c d phi by dt, this will become 1 by c squared d squared phi by dt squared. These will become identical equations, and these are the wave equations. Can you see that? So you have 1 by c squared d squared by dt squared minus del squared of either A or phi will be equal to 0. And you can, I hope you all know that these are wave equations, right? Let me write it down once more. So if you substitute, you will get both the equations will come to be 1 by c squared d squared by dt squared minus del squared of either phi or A, doesn't matter, equal to 0. So for example, phi will be equal to e to the I k dot x minus omega t. This is the wave number, this is the omega frequency, h cross omega is the energy, and k by omega is the velocity, which will here be c. If you put back mu naught epsilon naught, you will get c is equal to 1 by root mu naught epsilon naught, okay? So this is your wave which is traveling at the speed of light. A will also have, so this is, let us say this is phi naught times something. A again will be A naught times same thing, okay? So that means when in the absence of external charges and currents, your Maxwell's equations are actually, the solutions of Maxwell's equations are just electromagnetic fields which are waves which are traveling at the speed of light, which I will not derive here, but you have to just find what is the omega by k relationship, you will get C, and then therefore this is the electromagnetic wave that people talk about, right? If you can also replace back in terms of E and B, you will also find that E and B are waves. So you don't have to say that they are waves only in A and phi, it's a little more algebra, but you will find E is also E0 e to the I k dot x plus minus omega t, and B is also the same thing, only thing they will be perpendicular to each other, that's why they are called transverse waves. So the phase difference between the E and B field will be 90, so that when one is maximum in X, the other is maximum in Y when they are propagating in Z. So this is a completely transverse field, okay. So all this I see that I cannot repeat all of this, but this is the highlights of what is important. So this is the wave equation. I can write it either in terms of A's or I can write it in terms of E and B fields also. And these equations now are important because I want to then find the manifestly Lorentz invariant version of these fields. You can see that, right? Already I have, you can see this, I have already got, because of these two equations, what is this? This is the 4-dimensional gradient, Laplacian, right? It is called box. Just like del squared is d squared by dx squared plus d squared by dy squared, which is called with a triangle, which is 3 dimensions. So this is called a box. Some people write box squared because it's like del squared, but people also write box. So you can have box of phi equal to 0, a box of A equal to 0, and now I know phi and A are actually components of my 4-dimensional vector potential, not vector potential, 4 vector potential A. So this becomes box A mu is equal to, and if I bring back that thing, I will get box A mu is equal to, I've been using alpha, so box A alpha is equal to J alpha. Nice, right? It looks so nice. Now, no, just throw away all your Maxwell's equations and remember like this, okay? But we still have to write F alpha beta because we don't know the relationship between this and the electric and magnetic fields. So we will keep going, okay? We have some more distance to go, but you see that it will get extremely simplified. So on this page, do I want to say something more? Okay, fine. Now, even though I have defined a gauge transformation, this is, by the way, this is a simultaneous gauge transformation. I have to simultaneously change both. Otherwise, if I change only one, either E or B will not be invariant, right? So this is a simultaneous transformation, but there is still a residual freedom in this. And the residual freedom is because you can see that this satisfies or you just have to do one more derivative and you will get this, okay. So I have introduced a completely arbitrary term lambda, some function, it's some function of x and t. I have added the gradient of that to A, I have added the time derivative of that to phi, such that I get this condition. And where do I get this condition from? I get this condition from the requirement that if I start out with d alpha A alpha equal to 0, I must remain with d alpha A prime alpha equal to 0. And this box lambda equal to 0 will satisfy that constraint. You can see that that also looks like a wave equation for lambda, right? Somebody, I don't remember who asked, you asked me this question about gauge invariance is a very different thing, okay? Gauge invariance will come in field theory. Here we are just saying that we are using the fact that there is freedom because your potentials are defined such that only derivatives of the potentials appear in E. So when I integrate these equations, when I integrate a d by dx, I get something plus constant, right? So those, I can always fix those constants appropriately. They will always be unknown or up to those constants. Only when I measure the physical E field, I can fix that constant, right? So because of this freedom, I can have a gauge choice. So this particular gauge choice is called the Lorentz gauge. There are many gauges that you can use. This gauge people like because it is manifestly Lorentz invariant. It's called Lorentz gauge. But the other thing is that you can use non-Lorentz invariant gauges also. The main thing is that you have this residual freedom which you can fix, and therefore there are two sets of constraints. So there is one set of constraints here, and then there is this second set of constraints here. Now there is some little bit of algebra still to be done, but I will give you roughly the interpretation. We know that the solution of these wave equations is that you have a transverse wave where the E and B fields are mutually perpendicular to each other and also transverse to the direction of motion. The direction of the electric field vector is called the polarization of the electromagnetic field. So you know that it has polarization in the x direction or y direction. If I take x plus Iy or x minus Iy, I get left circularly or right circularly polarized light. You know that light can be polarized, right? So the electric field vector is what is the polarization vector. In fact, if you take the Fourier transform of the electric field vector, that is actually the polarization vector. That E itself is the polarization vector that will give you the direction of spin or whatever the polarization of that object. Okay. Now what happens is that because you have a transverse wave, the photon is a massless particle. I am now making just statements. I am not going to show you any of these things. It has only 2 degrees of freedom. It can have spin. Suppose it is moving in the x direction. It has spin, that is the electric field can be in the x or it can be in the y. Now we had a wave equation which had 4 components, right? It had phi, ax, ay, az. But the degrees of freedom for a transverse wave are only 2. And this gauge conditions therefore, and the subsidiary gauge conditions remove these extra degrees of freedom and make sure that you have a transverse wave which has only 2 degrees of freedom. Is it clear? So this is why it's not an accident that this happens. It happens because you actually have a massless transverse wave which actually corresponds to an electromagnetic particle called photon. I mean, when we do quantum mechanics, it gets quantized E is equal to h nu, right? So that is the photon wave packet, but it will still remain transverse as a wave, and therefore that 2 degrees of freedom will go away. And you will see it later when you talk about quantum mechanics or relativistic quantum mechanics, that this massless particle which has only 2 spin degrees of freedom, therefore will have to have 2 constraints to remove the other 2 degrees of freedom. Okay. So far I have only talked about these inhomogeneous equations. These homogeneous equations we keep forgetting, but we will come back to them later, and I will actually take it up in the next class. So this is, I went slower than I thought. I think I will, since I have said so much, I will talk about some more Lorentz invariance quantities. I will talk about energy, I will talk about the Poynting vector. I think that for people who have not seen electrodynamics, I don't want to leave it in half. I will apologize to all those of you who have seen it before, but I will complete at least. So what I want to show you is that the electromagnetic wave is actually a genuine object. If you can think of it as a particle, because it has energy, it has momentum, it has angular momentum, and there are conservation laws for all these. Just like you have in mechanics, classical mechanics, even if you take Newtonian mechanics, energy, momentum, angular momentum are conserved. The same thing you can define quantities for the electromagnetic field. It has energy, it has momentum, it has angular momentum. Okay, and these quantities also, it's good for you to see what they look like, because they will all be in terms of E and B or in terms of J. So let us look at all of them, so that at least some completeness will be there. So tomorrow maybe I will just spend some 20 minutes or something like that on completing this. Yeah, I think that it will just take some 20 minutes to do that, and then after that we can go back to writing all of it in terms of our 4 vectors and tensors. Okay, and that will only be tomorrow. So in the last class what I will do is I will actually do a Lorentz transformation. So I will take a point charge at rest in one frame, and then I will move it to a relativistically moving frame, and let's see how that looks in the 2 frames, and then I will finish over there. Okay. Okay.